What's the Doppler effect? In a single sentence, the Doppler effect or Doppler shift is the apparent change in the frequency of the wave due to the motion between the source of the wave and the observer. It was first introduced by an Austrian physicist, Christian Doppler, in 1842. In this video, we'll try to go in the depth of the single sentence. If you are interested to know it more visually, then please keep watching it. To observe the Doppler effect more physically, we have to understand the nature of a wave that is emitted by a source. Here, we will consider the source only a point source, of course. In this three-dimensional world, a source of a wave that may be light or sound wave, whatever may be. If this source is similar to a point source, that will emit spherical wavefronts or wavelets in equal time intervals. If the speed of the wave is v meters per second, then after 1 second, the radius of that spherical wave pulse will be v meter. But in this video, we will consider this pulse as circular wavefronts to make it more easier to understand. In reality, it could be a fire truck emitting sound, a car blowing its horn, a loudspeaker emitting sound, a duck creating ripples on the water of the pond, a star emitting light pulses just like this. But here, these objects are stationary, so the wave emitted don't show Doppler effect until the object move on. The sound that you hear gets out from a stationary object will be in the same frequency and so that in the same pitch. If the source object emitting waves comes towards the stationary observer, the wave towards the observer bunch up more and more. It comes closer to the observer and the waves realized by the observer at higher frequency. If the source goes away from the observer, the waves spread out more and more and it gets away from the observer and the waves realized by the observer will be in the lower frequency. Let's try to understand this with an example. Think you are standing by a railway track on this road. Yeah, that's you. At that moment, a train blowing its whistle comes towards you and then passes by, just like this. If you point out this more visually, you will see that as the train comes towards you, the sound becomes more and more clear and louder, and also the sound fades away from more and more it passes by. Here, the train whistle emitting sound comes towards you and the sound waves towards you bunch up and becomes more and more dense. It comes closer to you and the sound is heard by you at higher frequency and of course in the higher pitch. If the train goes away from you, the waves spread out more and more as it gets away from you and the sound heard by you will be in the lower frequency and of course in the lower pitch. If you imagine a graph by plotting the intensity of a sound versus time, you will see a bell-shaped curve will appear here and the peak of the curve will be higher at the position you are standing in. Now consider the Doppler effect for the light waves. Think you are in the observatory and observing the motion of this special kind of Death Star pulsar. The main feature of this pulsar is that it emits light pulses periodically, just like this. For this reason, pulsars are often called sometimes the lightest of this universe. If the pulsar comes towards the Earth, then the light pulses emitted by it will bunch up and more, and you can see the light comes from the star is in the higher frequency. And if the star gets away from the Earth, the light pulses emitted by it will be spread out more and more, and you can see it in the lower frequency. But here the question are, what does it mean by change in frequency here? And what will you see in higher and lower frequency of light? Because it is not the same like the change in the pitch of the sound waves. To answer this, we have to take a glance on the spectrum chart of electromagnetic waves, as the light is that kind of wave. In this chart, you will see in the visible region of light, the high-end frequency tends to the blue region and the low-end frequency tends in the reddish region of the spectrum chart. So, if any astronomical object is coming towards us, then it's called a blue shift, and it's getting far away from us, it's called red shift. But the most notable thing is that for light, the Doppler effect differs slightly from the classical effect in pleasing manner, because here we have to take in account the relativistic effect due to the extreme speed of light. According to the Einstein's special theory of relativity, the period of light pulse to the observer gets affected by time dilation. I will try to cover this time dilation and how it affects the Doppler effect in any other episode. For astronomers and astrophysicists, the Doppler effect provides an invaluable tool for measuring the speed of far-off objects by the shift in spectral wavelengths they emit. All our knowledge about how fast the universe is expanding comes from the observation of the Doppler effect in spectral lines. So that's all for today. I will see you in the next video with a more interesting topic in physics. If you like this video, don't forget to like, share and subscribe my YouTube channel for the latest updates, and kindly share your humble opinion in the comment section. That will help me a lot for my improvement. See you later my friends. Goodbye. Ta-da.